So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. Yeah? And this afternoon, it's a big pleasure to introduce to you Dr. Sydney Kasongo. Sydney is also a recent NITheCS associate, yeah, and belongs not to the traditional NITheCS discipline, theoretical physics, but he's more, as the title of his talk suggests, more a data science, machine learning guy, yeah, if I can say so. Yeah, and Sydney was born in the south of the Democratic Republic of Congo, in a small mining town called Likasi. But he studied, from what I gathered, in South Africa. He did his bachelor's in computer system at the Tshwane University of Technology. And at the same university, he did his MTech degree in computer science, cum laude. That was in 2017. Then for his PhD, he moved to the University of Johannesburg, and he completed a PhD in electrical and electronic engineering. And half a year ago, he joined the University of Stellenbosch, where he has a joint appointment in industrial engineering. And please correct me if I get it wrong, because
that's right. Yes, that's right.
And in this new school of data science and computational thinking. Yeah, and we just discovered that he's a passionate Formula One viewer. So yesterday afternoon, he was not busy preparing the talk, I guess. Yeah. Okay, Sydney, we are very happy that you're with us. And if you would like to start sharing your screen, if you prepared some slides for us, you're most and welcome to do so. And while you set up, I would just remind the participants to please make use of the Q&A facility to ask questions, or maybe just raise the hand and we can give you later the right to speak. Yeah. So Sydney, if you would like to start with your presentation, you're most and welcome.
All right, thank you so much, Francesco. I just want to share my screen now. I'm gonna switch off my video just to save the bandwidth.
Okay, I will do the same. We could see your slides, Sydney. They just disappeared again. Yeah, you just need to go into the presentation mode, pressing the
Can you see it now?
full screen view.
Francesca, can you see it now? Or
Yeah, now it's in full view. That's perfect now. Thank you so much. Thank you.
Just one second. I'm just gonna remove the audio there, because I prepared it with the audio.
Okay. Okay, but now we lost again your slides. Are you still with us, Sydney? I think Sydney is muted.
Yes, I'm here.
Yeah, okay, sorry. Yeah. Here we go.
All right.
Perfect.
All right. Welcome, guys, to the NITheCS Colloquium. And today I'm going to speak about the genetic algorithms applied to intrusion detection systems. I'm Sydney, as Francesca said, and the whole presentation. So I'm just going to start with showing you a background on intrusion detection systems. And just basically, intrusion detection systems are systems that are used in computer networks, you know, to protect computer networks against various type of attacks and against a lot of form of threats and stuff like that. And as you can imagine, in the current world today, with big data and all the financial transactions and e-commerce and stuff like that, I think such systems are going to be more of use compared to the past, right? That's just the definition. And there are a lot of types of intrusion detection systems, but this is just an overview of a high level, this is just an overview of a high level categorization of intrusion detection systems. As you can see, the base ones, the host-based intrusion detection systems, you can imagine such systems as one that is installed on your phone or perhaps on your personal computer, right? And then there are network-based intrusion detection systems. Those are the ones placed on a network. As an example, could be, let's say you've got a Wi-Fi network at home and you've got an intrusion detection system installed or that is pre-built into your Wi-Fi router, all right? And then you can have hybrid-based intrusion detection systems. And such systems, you know, they have a combination of intrusion detection systems on the network level and then on the on the host level. And such systems are sometimes called distributed intrusion detection systems. And these ones are the most common in use because there's a lot of distributed computation happening lately, right? Okay. All right. Now, on a granular level, you find different types of intrusion detection systems. So you've got the signature-based intrusion detection systems, anomaly-based intrusion detection systems, and hybrid-based intrusion detection systems. You can think of a signature-based intrusion detection system as a system that, you know, there's a pre-built database, right? And that database, each time there's an attack, we record the type of attack that happens. And then if that attack or intrusion or security threats happens again, then we just flag it, right? And the anomaly-based, it just compares the correct functioning of a system versus an incorrect functioning of the system and flags that as an intrusion, right? And then you've got hybrid-based intrusion detection systems, which is a combination of the two above. And currently, in current days, most of the intrusion detection systems are hybrid-based. So there's a signature-based, there's a database with signatures, and then we have the anomaly function on top of it, right? And today I'm going to introduce you to another form of intrusion detection systems, and such intrusion detection systems are based on machine learning, right? And the reason why intrusion detection systems based on machine learning are becoming more prominent today is because of the amount of data that exists currently, which means we can train any kinds of model for any organization depending on the type of traffic network that they have, right? So machine learning based intrusion detection systems obviously have been introduced to improve on the shortcomings of traditional IDS, the ones I've mentioned, the signature based, the hybrid based, and so forth. And these intrusion detection systems are very interesting because they make use of machine learning. And as you know, machine learning computer programs or computer software do not really need to be programmed or being told to do something. You just teach it to do something once, and it deduces from the training process that's going to happen. And such systems generally require you to build them on robust data sets. And today's data sets generally are really large in terms of the volume, the size of the data set themselves, and also in terms of the dimension of the data set. So machine learning based intrusion detection systems are very, very interesting, right? And today I'm just going to speak about a case study of one of the research papers that are recently published, and it used a genetic algorithm, all right, applied to an intrusion detection system data sets, you know, in order to select the best features in that multi-dimensional data set, and to see if that has a good impact on the performance of the machine learning based intrusion detection systems. And for this case study, I'm going to be speaking about the UNSW NB15 datasets. it's not a recent data set, but it's a very good benchmark to start off with. And another benchmark data set to start off with, for instance, the NSL-KDD knowledge and discovery data set, which is a very old one, but still a good benchmark. You've got the bot IoT. It's fairly recent, but not too recent, but it's fairly recent in comparison to the NSL-KDD. And then you've got the TON IoT, which is the most recent one in terms of IoT and industrial IoT systems. So in this case, I use the UNSW-NB15 because the mode of data collection is applicable to industrial IoT as well. And the reason why I selected industrial IoT is because, you know, with today's world, the IoT has grown into a bigger ecosystem. So we've got traditional IoT, right, whereby you've got machines talking to the internet, you've got, you know, devices on the internet, you've got software on the internet talking to each other. But with the industrial IoT, it's even bigger, where you've got, you know, from your home, you can check what's going on into, for instance, your business, into, you have a mining business and you're controlling this, your supervisory control and data acquisition software system into your mine through your phone, or you can access a sensor in your plant while you're in bed, you know. So the industrial IoT is a bigger ecosystem. That's the reason why I chose that case study. And as you can see, this is just a basic, not really basic as such, but just an overview of the industrial IoT architecture. And as you can see, you've got different layers in the industrial IoT. Like right now, I spoke about, for instance, on the perceptual layer, you've got things like tracking devices or card readers when you want to access university buildings or workplace buildings. You've got the application layer, like I spoke of, supervisory control and data acquisition software systems in mines, for instance, or smart manufacturing in vehicle assembly lines, for instance, like at BMW, Mercedes-Benz. And then obviously you've got the network layer. And I spoke already of your Wi-Fi router, for instance, you know, that's the network layer, but it can go even bigger, where you've got different type of communication protocols and stuff like that. All of this is the industrial IoT, but it goes even further. If you want to implement analytics and, you know, and control through the clouds, you can use AWS or GCP, then the industrial IoT even expands to the cloud. So you can imagine such an architecture can generate large amount of data, and such data, all right, it's multidimensional, and multidimensional means there's a lot of features into the data produced by such systems. And in such systems, you don't only find, for instance, a sensor that sends, for instance, temperature and volume, for instance. No, you find some sensors that send strings with so many features, some of them with little features. But now, how do you determine which features are important when you're building an intrusion detection system for such an architecture? Actually, that's the goal of the work. The work was, okay, you've got a system like this, you've got a data set that's generated by such system. How do you build an intrusion detection system that actually has the capacity to select the most important features, number one, because it reduces complexity. And number two, by reducing the complexity, do you increase the performance by doing that, right? So yeah, that's the case study. Now, genetic algorithm. Now, the genetic algorithm will be run on a data set that will be generated by such an architecture. And this is just a general overview. I'll show you towards the end the real implementation of this in Python. So the genetic algorithm is an evolutionary type of algorithm, a bit like particle swarm optimization or ant colony optimization. These algorithms are methods that are inspired by biological principle, literally inspired by what happens in the biological body in human beings or sometimes animals, right? So basically an optimization technique that is applied to the UNSW-NB15 dataset that we're going to use today. And you just have to keep in mind that these are the most important steps when you want to implement the genetic algorithm are the following. You have to be able to initialize a given set of population, so which means the parent of the next set of solutions. So the initial set of solution, if I can call it that way, and then those set of parent can give more solutions that are more optimized. It's like the parent giving the children more intelligence from the father and the mother, right? And then you have to be able to compute a fitness function. So the fitness function determines if a candidate solution is actually an optimal one, right? And you have to be able to conduct a crossover, you know, it's sort of like, it's a bit like a mixing, and then you have to be able to conduct mutation. And as you can see in the flow, I call it flow chart. So we applied the genetic algorithm onto the UNSW NB15 dataset, and then you have to do that in iteration, because this optimization algorithm has got an infinity of solutions, especially if you have a lot of features. There's a lot of combination that can happen, but you need to select the most optimal ones, right? So yeah, this is the genetic algorithm in a nutshell, right? And the framework that I've used, I can call it a workflow for the implementation of the genetic algorithm onto the UNSW 15. I'll go back onto the fitness function, right? So basically, the most important part, as you know, in data science is data cleaning. So we obtain the UNSW NB15, we pre-process that data set, and then we extract the training set, validation set, and testing set. And you'll see this is not really common, because most of the time you find in data science or machine learning problems where the separation is just the training set and the testing set. But in this instance, I also have the validation set, because I'm using the UNSW NB15 training and then the UNSW NB15 testing. And those two data sets come from a different distribution, which allows me to actually separate the main UNSW NB15 data set into two sets. And the validation set is actually used for sanity check. And the result that you get on the validation set have to be almost equal to the results that you find on the training set, right? That's the reason. And as you can see, they come from the same distribution. Obviously, this is the most important step. So you pre-process the data. Now, once the data is clean, then we use the genetic algorithm with the random forest machine learning algorithm. The reason why we use the random forest machine learning algorithm into the GA algorithm, it's sometimes people don't really clean the data as such, and algorithms such as decision trees or extra trees or random forest algorithm are sort of immune to things like data normalization and stuff like that. So that's one of the reasons why we have a modified version of the genetic algorithm in the fitness function. We use the random forest algorithm. And that algorithm will determine if a candidate feature vector or candidate solution is optimal by using the accuracy that it obtains onto after the training function has happened into the fitness function. And this is going to be done iteratively till the candidate feature vector is found. And when the candidate feature vector is found, then it is fed to other classifiers. In this instance, you can actually use the same random forest. You can use extra trees. In this instance, I use random forest, extra trees, decision trees, but it's not the only ones that you can use. You can also use other algorithms to make sure that you're getting a good result. And as you can see, the algorithms after training are being tested using a testing set. And the testing, you must ensure that the testing set, right, is really isolated from the validation set and the training set. The reason for that is you don't want data leakage. You don't want any data leakage to happen. And this happen iteratively as well, because there are many candidate feature vectors that can go to, I don't know, depending on the metrics that you've set for yourself, you can select 10 of them or 20 of them. And yeah, you test them using this framework. So this is a general framework that you can apply for anything else. If you decide to change the G algorithm and use the particle swarm optimization or the ant colony optimization or gray wolf optimization and stuff like that, or any form of optimization techniques for feature selection, you can just unplug the G algorithm and the RF, or you can leave the RF as a fitness function and then use something else instead of the G algorithm. But the G algorithm seems to be really efficient, right? So this was done over the WNB15 dataset, and some of the results, I'm going to show you some of the results. Some of the results that we run on a feature vector. This is a candidate, like F3 over here is a candidate feature vector. Now, as you know, the UNSW NB15 is a network related data set, and you've got things, features like duration over here, you've got features like service, you've got a feature like bytes and stuff like that. So after running the genetic algorithm, there was a lot of features that were selected, but this is one of the most optimal feature vectors, sorry, or this will be called a candidate solution. So called F3, and 16 features were selected out of 42 features. And these features were deemed to be the most important features after the genetic algorithm was run onto the UNSW NB15. And using this feature, this candidate feature vector, we ran the following machine learning algorithm: logistic regression over here as LR, decision tree as DT, and the random forest algorithm as RF, extra trees as ET, and extreme gradient boosting as XGB using F3. And as you can see, the best performing algorithm, at least in terms of accuracy, on the test set, is the random forest algorithm. And it was to be sort of anticipated because the random forest itself was used into the fitness function. So somewhere, somehow, it actually detects automatically, because at that point it was in the fitness function. But then now, after the candidate feature vector has been selected, then you pay to the random forest again in a sort of wrapper-based kind of setup. Then it produces a high accuracy, but it's not enough to look at the accuracy. You also, especially for such systems, you also have to look at the, the AUC, which is the area under the curve of the receiving operating curve. So this area beneath this curve, for instance, let's take the funny red curve generated by the logistic regression. I can see that these results in the grid here are validated by the result on the graphs. You can see that the logistic regression is not a really good machine learning algorithm for such a problem, but you can see that the random forest and the gradient boosting, which is the extreme gradient boosting classifier there, they have an AUC of 0.98, which is really good because actually a perfect AUC is 1. But then if you can get for at least for intrusion detection system, a classifier that can produce a close to 1 AUC, and you look at the accuracy and you look at the recall and the precision, everything seems balanced, then this is a good intrusion detection system. Obviously, there's room for improvement because this data set is a bit old, but it is a good benchmark, like I said, and some further work are being done using the TON IoT to see if these results can be beaten, and to see if this pattern can be verified, to say that, okay, using the genetic algorithm with a tree-based method, which is a random forest in this instance, or any of the other tree-based method as the extra tree or the gradient boosting classifier, is actually a very good idea in terms of selecting feature vectors that are to be used for detecting intrusions. All right, so this is the theory part. Thank you so much. I hope I was not talking too much. I just want to show you some practical implementation of the algorithm itself. I'm just going to close my screen now and share another screen.
Okay. We've got a question.
Yes, I can take a question.
Okay.
Yes. Could you explain on genetic algorithms? What features of genetics inspires the algorithm?
All right, cool. I will do that just now.
Thank you.
Can you see my screen?
Yes, we can.
All right.
Yeah.
This is actually a practical implementation of the genetic algorithm, right? For programmers, this is written in Python, right? And to answer the question, as far as I understand, the question is which features are being inspired for the genetic algorithm? Is that correct?
Yes. Which features of genetics inspires the algorithm?
Can you repeat that?
What features of genetics inspires the algorithm?
Oh, okay. All right. Well, the features of genetic that inspire the algorithm is the fact that, well, the algorithm itself is inspired from, like, a man and a woman giving, birth to a set of children and giving them the best features of their DNA, if I can put it that way. But that's just not on the DNA level, could be anything else. But at least in this instance, like I said, you've got an initial population. In that instance would be the parents, and the parent gives birth to the children, and the children can also give birth to children, and the grandkids carry better features, if I can put it that way, in comparison to the parents. So I think that's actually the genesis of the whole algorithm. I don't know if I answered your question.
I hope so, because if anonymous attendee who's asking that question is not satisfied, he can give some clarifying questions. Thank you.
No problem. Okay, so this is the practical implementation of the genetic algorithm. And as you can see over here, I hope it's big enough. Let me just magnify a little. As you can see here, this is a whole, I don't want to bore you with the data engineering part of things, but all you just have to know is the training set and the testing set were, imported. That would be the training set over here, and then the testing set over here. And then there's a whole data engineering happening there. And most important thing to note is the features. All these are the features of the name. Feature names are literally of the UNSWNB15. And this is a theoretical sort of data set, right? And features can go into thousands, can go 1,000, 2,000 features. But obviously for testing the algorithm, these are the features of the UNSWNB15, right? And like I said in the slide, like I explained in the slide, you have to be able to initialize the initial population, right? You have to be able to conduct a single point crossover, which is a method that allows me to cross over different set of solutions, right? And you have to be able to flip the mutation. You have to be able to have a mutation possibility into your algorithm. And there has to be random selection, because if there's no random selection, then there could be some bias into your algorithm, right? And now the modified portion of this algorithm is this fitness function. This fitness function is very important because that's the function that determines which candidate feature vector is actually good or not, right? And this feature function, the fitness function, has another function inside, which is a predictive model. So the predictive model in this instance is a machine learning model. And in my case, I use the random forest classifier, which is the one here is the one from scikit-learn, which is the machine learning framework. But the beauty is these two functions here are highly customizable. So you can change them depending on the kind of problem that you have, right? And then once all of that has been built, like in this instance, then obviously this is more for optimization. And then this is to ensure that, when you have twins, in a sense, where you have a duplicate solution, call them twins, then one is removed, right? And the whole set of functions up to the top there is actually embedded in what I call GA, which is a genetic algorithm functionality. And obviously, this genetic algorithm has to have input as data. the second input is the feature list. When you go up is the number of features that you've got in this list. In this instance is 42, I think 42 or 45. And obviously the target now determines if your modeling was done using multi-class classification or binary classification. And then the N is the number of initial population, all right? The number that you're gonna start off with, your algorithm, up to when you're going to get an optimal solution. And then there is the maximum iteration, how many times you want the algorithm to run, right? So that's basically it. You don't have to worry about that little details. So as simple as that, all you do is, let's assume this is a library. All you have to do, you don't even need to worry about any of these functions up there. All you do, unless you want to change the predictive model and the compute fitness function, all you do is you just call the genetic algorithm there, right? Now in this instance, I actually pre-run this because it takes sometimes a lot of time. So you call the GA, right? And then you call your data in this instance, and then you input your feature list. And then in this instance, I use multi-class classification, which is attack category. And then initial, I want 4 individuals, and then I want it to run for 2 iterations. And the results was this feature vector over here. Obviously, you have to run an algorithm to count this list to find how many features are in there, and then take this list and feed it into another algorithm to find out the solution. So the optimal accuracy here is generated by the random forest. But obviously, I only run it on 2 iterations. And ideally, this is the number to optimize. We want it to be close to 100, which is really good. I mean, if you run it for longer, you can get into 95, 98, and that's how you actually get these feature vectors. So as you run them, then you feed them into another algorithm to get the result. Yeah. All right. Any question about this implementation of the genetic algorithm using Python?
And please, you're welcome to raise your hand, and we can give you quickly the right to ask your question in person if you want. Yeah. Sydney, here there's Victor wanted to ask a question, and I think there is also a question in by Emmanuel.
There is a question.
Yes, Victor, just a second.
Okay.
I will just give Emmanuel the right to talk as well, so he can ask his question in person. Victor, please go ahead.
Okay. Doctor, please, my question is this. How can the quality of your findings or your answers be improved over time? Can you hear me?
Yes, I can hear you. So the quality of
your findings or your answers, the optimal values we have, how can it be improved over time?
Improved over time. They can be improved over time by running the algorithm onto newly created data set, because intrusion detection data sets are really rare to find. So how do we improve this algorithm? Let's say Microsoft today comes up with the algorithm of all that happens using, for instance, malware detection, stuff like that. We can literally take this algorithm and actually retrain it on that data set and see the result that we find. And we can obviously use different optimization technique in the fitness function, for instance, to improve the data set. So it's a matter of having a good data set to test the algorithm on, and then have that data set as a benchmark for further network attacks. And just note, this is also applicable to live data. So you can literally use such algorithm on live data as well. So.
Thank you. The second question is this. What specifically does one need to avoid in implementation as not to make the algorithm converge to a solution that is not optimal?
Number one, the first problem is at the data level. You've got to ensure that your data is clean and there's no bias. That's number one. Number two is you have to ensure that in your fitness function, when you do predictive modeling in there, you must ensure that there's no overfitting. And if there's a phenomenon of overfitting in there, then in your machine learning modeling portion of the algorithm, then that could lead to a problem of not converging to a proper, yeah. So you must ensure that there is no overfit.
Thank you so much, Doctor.
There was a question by Emmanuel in the chat. Emmanuel, would you like to ask your question in person? You just need to unmute yourself.
Thank you. Thanks, Sydney. Thanks for the talk. Maybe my question is silly, but I'll ask it anyway. Given that the people who are interested in developing these intrusion attacks, they probably will be aware of the intrusion detection systems. So is it possible that those who are working on the attacks, given the knowledge of the systems put in place to detect the attacks, can that result in more sophisticated attacks for which algorithms might not be able to detect? In other words, this is like the analogy of adversarial attacks on intrusion detection, and if you think that this could be the case, that those conducting the attacks are producing more and more sophisticated attacks, given that they have access to academic literature, for example, what do you think is the future of these intrusion detection systems?
Well, you're actually right. The people who have actually access to such research work can actually engineer methods to, build more sophisticated attacks to actually attack such systems. I think for me, the future is, it's very hard to build online intrusion detection systems in a sense where it actually trains on live data at any given point in time, right? But I think with things like quantum computing and faster infrastructure, that would be possible. Then even if these people engineer new attacks, but because the intrusion detection system is training on live data, then there's a chance that it saw something and then it learns the pattern, then it flags whatever new attack that's, I think that's the future, that's where it's going. But as far as this one is concerned, the people who've got access to such knowledge can actually engineer some attacks that can actually go through as legitimate, traffic patterns or transactions in a sense.
Thank you.
Thank you. And Sydney, there's a question by Timmershen Achery that I just promoted to speaker. So Timmershen, if you would like to ask your question, you're most than welcome. You just need to unmute yourself.
Hello. Yeah, I wanted to find out, given the data set, how long does the framework take to compute the fitness of a solution? Like I provide an example, like for 100 iterations, what would be the length of the runtime?
Actually, I'm working on the analysis of the times because I was worried more about the accuracy that it produces. But for argument's sake, I know with 1620, you do that in less than 10 minutes, depending on the number of code that you have on your training machine or number of GPUs that you have, but less than 10 minutes, 1620. So I'll say less than 20 minutes in that instance. But obviously, I just have to run more analysis now in terms of complexity and how to reduce that complexity now. I think that's another set of problems. But yeah, because I run that not on my laptop. My computer, my home setup could not run that. So I had to use Google infrastructure and a little bit of AWS. So I think the next step will be to study the complexity now of this piece of software and see how to reduce it.
Yeah, thank you.
Thank you. Are there more questions? Please, if you have more questions, just raise your hand. There is one more question. There's a question by Makamisa Senekane. Makamisa, I give you the right to talk. You are welcome to ask your question.
Thank you very much, Prof. Sydney, my question concerns the data set. Isn't it that the IDS data set is normally imbalanced with more cases of the negative and fewer positive cases? And if that's the case, how do you deal with that imbalanced data? Is there any way you're treating that? Because if it's not treated, it might affect the accuracy of your model. Because if you train it with more negative cases and fewer positive cases, it might memorize the negative cases more than the positive ones. Is there any way you're dealing with that in your model, in your algorithm?
Yeah, not in this specific body of work, but there's another body of work where I'm using a synthetic method for oversampling. So what you do is you just oversample negative classes. Well, in this instance, I suggest negative classes are intrusions and positive ones are not in that sense. Then I oversample the minority class, but that also could have an impact because then the algorithm could be sort of a little biased towards the other side of the algorithm. So I'm working on that using an algorithm called SMOT, synthetic. It's a synthetic oversampling technique. So that's how you can deal with that. But now the beauty about this genetic algorithm, when you look at metrics, when you look at your AUC and you look at your precision, you can see actually that even the minority class, although a minority, but they are being detected. So by the time I oversample, I think my assumption would be that actually the performance is going to increase. But already with the genetic algorithm, I know that the AUC is good, the precision is good, which means then I'm already getting a good rate of detection on intrusions.
Thank you, Sydney. And there is one more question by Muwawa. Please, Muwawa, you can unmute yourself and ask your question in person.
Okay, thank you. Dr. Sydney, thank you for the presentation. Can you hear me?
Yes, we can hear you clearly.
Can hear you perfectly.
Yes. My question is more on the practicality of the algorithm. Has the algorithm been tested on real network traffic? And if yes, how good is it in detecting false positive? Because one of the problems that antiviruses and advanced threat detection systems are having is false positive. How is the algorithm provisioned to deal with that?
Thank you, Muwawa, Jean, for your question. Look, this algorithm on at least the UNSW NV15 was actually, it's a paper that was actually published sometimes last week or last week. So I haven't got a chance to do it on real live data, but that's the plan. The plan is to have it on, let's say, a university sub-network and find out if the algorithm is going to perform optimally. So we literally forcefully run a small attack onto a closed Wi-Fi network in a university building and see if the algorithm perform optimally. I think that's where we're going with this research, but this is really fairly recent. I think as of last week in IEEE Access. So I think that the goal is to actually have, first of all, the small technique applied to this work, and then now have it on live data and see if it performs optimally. I think the live data portion of these intrusion detection system is actually the biggest work, and resources have to be put in there for more research to be done to get more robust intrusion detection systems.
Thank you. Thank you for the answer.
Right.
And if you can allow me to make a small comment, I don't know if I'm allowed.
You're most than welcome.
Yeah.
Oh, thank you. So this is in regards with Emmanuel, Mr. Emmanuel's comment, question. It was really a very important question regarding the perceptive of the attackers, because I'm an academic and I'm also working in the industry in the area of threat intelligence. So we have to also know that, as Dr. Sydney said, AI and ML are not only being used by defenders, attackers as well. With more advanced APTs or advanced persistence threats, we see that now that threat actors are now making orchestrating attacks or making malwares that adapt to the system and can detect the presence of AI-based defense and can bypass that with other sophisticated technologies, especially threat actors that are nation state sponsored, or cybercrimes with a lot of budget. You can look at the recent attack with the Pegasus. You'll see that the techniques, the capabilities, and the tactics used are really, really above what we have all known so far. So the same way we are trying to become smarter in defense, attackers as well are becoming smarter. So, and one of the projection or the solution that most researchers are looking at is in the area of threat intelligence and threat hunting. So trying to be a step ahead of the attackers by studying the previous TTPs and anticipate how they can modify that and be able to stop that. Hopefully we get to that point. I just wanted to comment on that part as well.
Thank you so much, Muawa. Thank you so much. Appreciate it.
Thank you.
Yeah, thank you very much. Sydney, it looks like nobody else has raised the hand to talk or posted questions in the Q&A. So it's now my pleasant task to thank you very much for your nice talk and for really giving us a nice insight of what happens behind the scenes of the Internet of Things, yeah? Because we take many things just for granted, but there is lots of activity behind the scenes to make sure that we are all safe, yeah, not only from the biological viruses, but also from other viruses, yeah? and other things, yeah. So Sydney, thank you so much. We will be very happy to follow your research in the future, and maybe in due time we will ask you to come and share with us again more recent and future research results, because you saw from the many questions and comments that this seems to be a topic that interests people, yeah? And it has to interest all of us because we all live in the Internet of Things so far. Yeah. So
thank you so much, Francisco.
Thank you so much, and thank you very much to the participants. We are looking forward to see you again next week. And thank you, Ilya, for joining as usual. And yeah, I wish you all a good evening, and please stay safe. Yeah. Thank you. Bye-bye. All the best. Thank you. Thank you very much, Sydney.
Thank you so much. I appreciate it. Thank you so much. Bye-bye.
Thank you. Bye.